Welcome to dxSudoku training video number 106. In this video, the puzzle-solving technique called Alternate Inference Chains will be demonstrated. Alternate Inference Chains, or AICs, are probably the nearest thing Sudoku has to a theory of everything. A theory of everything meaning a universal puzzle-solving technique for candidate eliminations. In this video, an additional technique of adding extensions to our AIC chaining sequence will also be demonstrated. An AIC extension can be any Sudoku puzzle-solving technique. These additional Sudoku puzzle-solving techniques are used for creating group nodes as part of our AIC chaining sequence. Here is a list of prerequisite videos for this video. Consider the following Sudoku puzzle loaded into Sudoku. Sudoku is rating this puzzle as extreme with a difficulty score of 2028. You can see the summary section showing the puzzle-solving techniques Sudoku's solver would use in solving this puzzle. We will use Sudoku's solver to get all the easy stuff out of the way. From Sudoku's View drop-down menu, we select the Solution Path command. We are now seeing the solution path for the techniques the Sudoku solver would use to solve this puzzle. We right mouse click over the W wing step in the solution path and select Solve All Before from the pop-up menu. Sudoku has solved the puzzle up to the W wing in the solution path. The W wing is now showing as the next hint in the puzzle. We hit the escape key on our keyboard and we are now ready to begin searching for AICs. The AIC technique demonstrated here will blow past any W wings. And besides, searching for W-wings are just as tedious as searching for AICs in the puzzle. When doing our AIC search, we are going to use Sudoku's candidate coloring feature. From Sudoku's View drop-down menu, we select the Active Cell menu command. Sudoku's candidate level coloring palette is now being shown in the lower right part of the application. The first step in our algorithm is for each number 1 through 9, we mentally create a list of potential starting candidates for our AIC chaining sequences. For this demonstration, I will list out all the possible AIC starting candidates. The reason we are doing this is because not every starting candidate is going to create an AIC chaining sequence having a positive result. Most are not going to do anything to help us solve the puzzle. We begin by highlighting all the cells having a possible 1 candidate. What we are looking for is any candidate participating in an either-or link relationship. As you can see, the possible 1 candidate in cell 4, 3 and the possible 1 candidate in cell 4, 4 have an either-or link relationship with each other. What this means is either the 1 in cell 4, 3 is on or set as the value of the cell, or the 1 in cell 4, 4 is on or set as the value of the cell. Both candidates can't be false or off, and both candidates can't both be true or on. This is because there must be at least one cell having a value of 1 in the house making up row 4. So we note both cells as having potential starting candidates for a successful AIC chaining sequence. Again, not all these starting candidates will have successful AIC chaining sequences, but when we start searching, all these cells we note here will be our starting points. Here are all the starting cells for the possible 1 candidate. Here are all the starting cells for the possible 2 candidate. Here are all the starting cells for the possible 3 candidate. Here are the starting cells for the possible 6 candidate. Here are all the starting cells for the possible 7 candidate. Here are all the starting cells for the possible 8 candidate. And here are the starting cells for the possible 9 candidate. We have a total of 38 candidates and cells we can use as starting points in our AIC chaining sequences. This may sound like a daunting task, but the AICs are extremely powerful, as you will see demonstrated shortly. So essentially, this list is every candidate in every cell participating in an either-or link relationship. The next step in our search algorithm is we pick a starting candidate and starting cell for our AIC chaining sequence. For no reason, we pick the first candidate and first cell in our list. As you can see, we have colored the candidate purple and we update our notes. What this is saying is we begin our chaining sequence by assuming the 1 in cell 4, 3 is false or off. I've updated our algorithm to include building out the chaining sequence. I've added a new set of nodes to the chaining sequence. There are actually 3 new nodes going off in 3 different directions. Each link added is a strong link based on 4, 3 colored purple and pretending to be off. Candidates are colored dark green to indicate that they are true or on in our chaining sequence. It may be only one or none of these chaining sequence directions result in anything useful in solving our puzzle. When you are looking for an AIC chaining sequence, we will try every direction until we find something useful. For many people, it's often confusing when they see an AIC chaining sequence in its finished form. The question is, how did someone come up with this sequence because it's not immediately obvious? The answer is, the chaining sequence went off in every direction, and what you are seeing is just the chains in the sequence that resulted in something useful. We just added a round of strong links to our chaining sequence. Next, I'm going to add a round of weak links coming off the candidates that were just colored in dark green. I've added the next round of weak links to our chaining sequence. I have gone as far as I can go with the possible 1 candidates. Now, before I move on to the next candidate, I want to point out something special about what we've done so far. Rather than go off in every direction, if we had chosen a single sequence path currently being shown in our notes, we would have a special case. Notice how we have a weak link from cell 7, 3 back to our starting cell 4, 3. This is a special case known as a nice loop. Whenever a nice loop occurs in our chaining sequence, we can eliminate other candidates in the puzzle sharing a house with a purple and dark green candidate from our chaining sequence. I've updated our algorithm notes for what to do when a nice loop occurs. However, with what we've done so far, there are no candidates that qualify as seeing both the purple and dark green candidate, so we move on with our search. All the cells having a possible 2 candidate are now highlighted in light green. Based on our current set of dark green candidates, we have 4 possible candidates we could add as a weak link relationship to our chaining sequence. We only add a weak link for the 2 in cell 7, 3. The reason we choose to only add this one weak link is because the 2 in cell 7, 3 participates in a strong link relationship with the 2 in cell 7, 1. We need to alternate between weak and strong links in order to keep adding additional nodes to our chaining sequence. The 3 other candidates not chosen were dead ends for our chaining sequence. Here's the next strong link added to the chaining sequence. At this point, we have a number of weak links to consider to add to our sequence using the 2 in cell 7, 1 as the first node in the relationship. Just as before, we want to add weak links that also have the possibility of strong links to continue our chaining sequence. The 2 in cell 5, 1 meets our requirements. A new weak link is added to our chaining sequence. We could have added weak links for the 2 in cell 4, 1 and the 2 in cell 6, 1, but because there's not a strong link out of either one of these cells with the 2, they are dead ends for our chaining sequence. Whereas the 2 in cell 5, 1 has a strong link to the 2 in cell 5, 4. The next strong link in our chaining sequence has been added. Take a closer look at cell 5, 4. We already had a 1 candidate colored purple, and now we have the 2 candidate colored in dark green. What this means is there's a weak link relationship between the 2 and the 1 in cell 5, 4. Having this relationship creates another nice loop back to our existing chaining sequence. And as before, having a nice loop will have consequences for the other candidates in our puzzle. Here's how to think about nice loops and their special powers to eliminate other candidates in the puzzle. As a chaining sequence, nice loops are bidirectional in the following sense. If any of the candidates highlighted in purple are removed because another candidate was chosen as the value of the cell, then all the dark green candidates in our chaining sequence become the value of their cells. And the same is also true if any of the dark green candidates is removed from its cell because another candidate was chosen as the value of the cell. If any of the dark green candidates are removed, then all the purple candidates become the value of their cells. You could easily prove this logic for yourself with any nice loop. So what this means for cell 5, 4 is the possible 9 candidate is a non-possible candidate. Because of the nice loop, cell 5, 4 will either have 1 as its value or it will have 2 as its value. I've updated our algorithm notes to include what to do when both candidate chaining colors show up in the same cell. We apply the new algorithm rules to cell 7, 3, and we find 2 more candidates that are now highlighted in dark red because they are non-possible candidates and can be removed. We removed the non-possible candidates from the puzzle. I found another special case I want to talk about. Consider the following group node weak link we just added to the end of our chaining sequence. If 5, 4 equals 2, then both candidates in our group node are false or off as shown. Also, notice how the 2 in cell 7, 3 is off as part of our chaining sequence. Now take a closer look at the 2 candidates in the 4 cells now outlined. The 2 candidates in these 4 cells form an X-wing. The X-wing will cause the 2 in cell 4, 1 and the 2 in cell 6, 1 to both be off or false. This is very similar to the X-wing or X node I demonstrated in dxSudoku video number 100. But in this video, instead of an X chain as our chaining sequence, we are using an AIC chaining sequence. The concept of using an X node as part of our chaining sequence logic for continuing our chaining sequence works the same. With this in mind, consider the following logic I will use for eliminating some candidates. If cell 5, 1 has a value of 2, then the 2 in cell 4, 1 and the 2 in cell 6, 1 are false or off. And if the 2 in cell 5, 1 is off, then our chaining sequence kicks in. And the X-wing we identified causes the 2 in cell 4, 1 and the 2 in cell 6, 1 to be off. So in both cases with cell 5, 1 on or off, the 2 candidates now highlighted in red are non-possible candidates. When using an X node this way in a chaining sequence, it doesn't have to be an X-wing. You can use any Sudoku puzzle solving technique as the X node. This is what I mean by having an extension to an AIC chaining sequence. In this example, it turns out there's an easier way to eliminate the same 2 candidates. Consider all the 2 candidates in the house making up column 1. Based on our algorithm rules, since both colors from our chaining sequence occur in the same house, all the other 2 candidates are non-possible candidates. The non-possible candidates are removed from the puzzle. Next, I'm going to demonstrate a second method for eliminating candidates using AIC chaining sequences. This second method is used when you cannot find any nice loops in the puzzle. Search method 2 is now highlighted in our algorithm notes. We are going to cycle through using every candidate that is participating in an either-or link relationship as the starting candidate for an AIC chaining sequence. We probably have about 30 candidates to try, but there are a few considerations we can use to help guide us in our choices for finding good ones with less work. All the cells having a possible 9 candidate are now highlighted. We begin by choosing a starting candidate for our chaining sequence. We currently have 5 choices, all highlighted in gray, based on the candidates that are participating in either-or link relationships. I decided to go with cell 6, 4 because it's a bi-value cell and it shares a house with 2 cells having possible 9 candidates. Next, we assume the 9 in cell 6, 4 is on, as indicated by it being highlighted in dark green. We highlight all the 9 candidates that would be off if cell 6, 4 had a 9 chosen as its value. We do not color the 9 in cell 4, 5 in dark gray because this candidate will be the first node in our chaining sequence. The 2 candidates colored in dark gray will be the candidates we will be targeting to remove based on the results of our chaining sequence. We begin our chaining sequence by assuming the 9 candidate in cell 6, 4 is false or off. And the first round of strong links for our chaining sequence have also been added. I'm going to go off and build out the chaining sequence. I'll be right back. I'm back. Since the 9 candidate in cell 6, 1 is now colored in dark green because of our chaining sequence, then the 9 candidate in cell 6, 9 can be marked for removal and is colored in red. We have the normal chaining sequence logic for why the 9 candidate in cell 6, 9 can be removed. If we have a 9 as the value of our starting cell 6, 4, then the 9 candidate in cell 6, 9 is killed. And if we don't have a 9 in cell 6, 4, the chaining sequence kicks in, and a 9 in cell 6, 1 is on, and this results in the 9 candidate in cell 6, 9 being killed. So in both cases, the target candidate is killed, so we must conclude it is a non-possible candidate. It's important to note that the candidates highlighted in dark green may or may not be the true value of the cell. This chaining sequence only has meaning in the context of the starting candidate assumed to be false. Since the candidates colored in dark green may not be the actual value of the cell, it creates a peculiar result which we will demonstrate in the next example. The non-possible candidate is removed from the puzzle. Here is the next chaining sequence to be demonstrated. We begin by assuming the 2 in cell 5, 4 is on. The 2 in cell 5, 1 is colored in purple because it's the first node in our chaining sequence. The 2 in cell 4, 4 and the 2 in cell 6, 4 are colored in dark gray because they are the candidates we are targeting to remove by our chaining sequence. We begin our chaining sequence. We assume the 2 candidate in cell 5, 4 is off or false. In case you are wondering, I chose the 2 in cell 5, 4 as the starting candidate after several other candidates did not result in anything useful. I'm going to go off and build out the chaining sequence. I'll be right back. I'm back. As you can see, our chaining sequence has resulted in the 2 candidate in cell 6, 4 as being a non-possible candidate. This is because the 2 candidate in cell 6, 9 ended up being colored in dark green as a result of our chaining sequence. Remember, the purpose of the chaining sequence is not to solve the puzzle. The only purpose of the chaining sequence is so that we have logic to justify the removing of a candidate from the puzzle. It turns out, in this example, our starting cell assumption is wrong in terms of the puzzle solution. This will create a peculiar situation with our chaining sequences. Here we have a second chaining sequence with the 2 in cell 5, 4 as the starting candidate. Notice how with this chaining sequence, the 2 in cell 6, 9 is not dark green or on. It's actually purple or off. When our starting assumption is wrong in terms of the actual puzzle solution, we could have multiple chaining sequences that are all incorrect in terms of the actual puzzle. But this is not a problem, since all we need is one chaining sequence that allows us to remove a possible candidate from the puzzle based on logic. Notice how with this chaining sequence, I ignored the 3 in cell 6, 1 because it doesn't help our cause. So with the possibility of multiple chaining sequences in mind, we need to create our chaining sequence with some insight. In this example, to be successful in removing a candidate, we needed the 2 candidate in cell 6, 9 to be highlighted in dark green. We can use this information to help us build out our chaining sequence so we have a positive result. If there are 2 AIC chaining sequences where one allows us to remove a candidate and the other does not, we choose the one that allows us to remove a candidate. All that matters with our chaining sequence is that we have a logical reason or argument for why a particular candidate should be removed. The non-possible candidate is removed from the puzzle. Before we continue solving this puzzle, let me put this video in context with my other videos. In video number 87, I demonstrated a technique using Bowman's bingo along with AIC chaining sequences having extensions. This technique works with a class of puzzles all having bi-value cells. The technique either solves the value for one cell or the entire puzzle is solved. The problem with Bowman's bingo is many people do not like it because they claim it is just guessing. In this video, I demonstrated using AIC chaining sequences with or without extensions as a way of eliminating candidates from the puzzle. This video only shows how to remove possible candidates from the puzzle. Once a chaining sequence is found that is useful, there is no guessing with the way the candidates are removed. As long as a puzzle has candidates participating in strong link relationships, AIC chaining sequences with extensions can be used to solve a very large class of extreme puzzles. However, Most ultra-extreme puzzles start out having no candidates participating in any strong link relationships. In video number 88, I describe a technique I call MVE. With MVE, multiple nested assumptions are made as an AIC chaining sequence is built out. MVE is a brute force-like technique using AIC chaining sequences along with AIC extensions to find a solution path to the most difficult puzzles. MVE is the only way I've found for solving the most ultra-extreme puzzles without using a computer program. Okay, back to solving our puzzle. There's a naked single with the 9 in cell 6, 4. We need to do one more AIC chaining sequence to solve this puzzle. All the cells having a possible 3 candidate are now highlighted. We begin by assuming the 3 in cell 8, 9 is on. The 3 in cell 6, 9 is colored in purple because it's the first node in our chaining sequence. The 3 in cell 8, 1 and the 3 in cell 8, 3 are colored in dark gray because they are the candidates we are targeting to remove with our chaining sequence. We begin our chaining sequence by assuming the 3 in cell 8, 9 is off or false. I chose this candidate because if the target candidates are removed, it will open up a lot of naked singles. As you can see, I added the first strong link to the chaining sequence. I'm going to go off and build out the chaining sequence. I'll be right back. I'm back. As you can see, our chaining sequence was successful. Both the 3 in 8, 1 and the 3 in 8, 3 are now marked as non-possible candidates. The non-possible candidates are removed from the puzzle. At this point in the puzzle, there's nothing but easy stuff remaining. I'm going to go off and clear off the easy stuff. I'll be right back. All the easy stuff is cleared off and the puzzle is now complete. My second Sudoku book is now available for purchase on Amazon.com. It contains 500 really interesting puzzles, plus a detailed diagram and explanation for 26 puzzle-solving techniques. You can use Sudoku Joy for the iPhone or Endoku 3 for Android devices to easily scan in and start playing these puzzles in seconds. Each of the 500 puzzles has a Sudoku toolbox showing you exactly what you need to know to solve each puzzle. I spent a huge amount of time finding interesting puzzles. As you can see in this example, both puzzles require finding 3 swordfish in order to solve it. Other cool puzzles include things like having to do 5 Extionsions in order to unravel the puzzle. Please support dxSudoku by purchasing one of my books on Amazon.com. This completes dxSudoku training video number 106. Thank you for your support and thank you for watching.